Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are now starting a first lecture for our week number 4. In today's lecture we will be starting the discussion regarding modulation. In our initial lectures we had a preliminary discussion related to modulation, and mainly we talked about why there is need of modulation in our system. And in today's lecture we will be focusing on how we achieve the modulation and how we represent the information in the modulated signal. So how the process is done and how the modulation is performed, and what is the mathematical way of representing the modulated signal. So this will be the discussion of this week's lecture. In fact, it will continue in next week as well. Before we start our discussion for today's lecture, let me quickly recall what we have discussed regarding the modulation so far. So we have previously discussed that the primary reason for using modulation is to create compatibility between message signal and the transmission channel. The main problem in the transmission channel is that it generally supports a specific type of frequency, a specific range of frequencies or a specific band of frequencies to pass through that. In order to have a good transmission quality, the message should be placed at that particular frequency, and message on the other hand, they are generally at relatively low frequency. In order to create this frequency compatibility, we need to shift the frequency of message signal towards a higher frequency band, frequency range, and that shifting or that frequency translation is achieved through the process of modulation. So basically modulation creates a compatibility by providing a frequency translation to the message signal. However, we have previously discussed that there are several other reasons which encourage us to incorporate modulation in the system. So this is not the only reason, although in most cases you would see the modulation performed to create the compatibility, but in many cases there are several other reasons as well. So basically the process of modulation, we generally have a frequency translation so that the message is placed at the desired frequency band. On the other hand, when we go at the receiver side, in that case we do not need that carrier which is carrying the information, and we remove that carrier on the demodulation side and recover the original message. We have previously talked that there are two major categories of modulation. One is called continuous wave or CW modulation, which involves a high frequency sinusoidal carrier, and this high frequency sinusoidal carrier is used to carry the information, and basically it provides that frequency translation, and it carries the information at relatively higher frequencies. So because of being at high frequency, we sometimes name it as band pass modulation, because our signal would be at relatively higher frequency band. On the other hand, there is another modulation scheme where we use pulses to represent the information. So we represent our message by using different pulses. So basically this is commonly used in discrete time systems. However, you should note that pulse modulation does not involve frequency translation. So actually it does not provide any shifting in the frequency. So that's why this pulse modulation is sometimes named as baseband modulation. So this was a quick review how this was a quick review regarding the discussion that we had previously regarding the modulation. So now let us start the discussion for today's lecture. So I would start my discussion by posing a question that how the information signal is superimposed on the carrier. So as we said that in modulation, there we superimpose the message signal onto the carrier, and that carrier takes that message signal or that information to the receiver side. So our question is how this superposition is achieved. So, or how we change the carrier in order to represent the message signal. So the answer to this question is that we have to change at least one parameter of the carrier. We change one of the parameter of the carrier in accordance with the message signal. So that change in the carrier parameter actually represent the information contents in the carrier. So basically, one of the parameter carries that information that is represented by the message signal. Of course, this answer is not complete, so we need to be more elaborative. So let me try to explain what I mean by changing one of the parameter of the carrier in accordance with the message signal. So let us start by identifying the parameters that we can change. So what are the parameters that can be exploited to represent the information contents? So for sinusoidal wave, that means for continuous wave modulation, there are three parameters that are available. You can see that we have previously discussed as well. In sinusoidal wave, a sinusoidal wave has a certain amplitude, it has certain frequency, it can have a certain phase. So basically we have three different parameters that represent the overall sinusoidal wave. In order to represent the information by using a sinusoidal wave, we can either change the amplitude or frequency or phase. Similarly, for pulses or pulse modulation, again we have three different parameters. Typically a pulse is characterized by its amplitude, its position where it is placed, and third is width, how wide the pulse is. So for pulses also we have three different parameters, its amplitude, pulse width and pulse position, that can be used to represent the information. So the first thing that I want to highlight is that we need to change one of the parameter of the carrier so that we can represent the information by using that change in the carrier. So let me now try to give some examples. So let us start with CW modulation or continuous wave modulation, where we use a carrier of sinusoidal wave. So let us assume that our carrier is given by this simple expression a cos 2 pi f plus ft plus phi. So sorry, I missed the t, I will correct it in the final version. So a cos 2 pi ft plus phi, so there should be t here. So you can see that it has amplitude, frequency and phase. As I mentioned that we can change one of the parameter in accordance with the message signal. So one possibility is that we change the amplitude of the carrier in accordance to the message signal or in proportional to the message signal. So how much change is there in the message signal, that should be reflected by change in the amplitude of the carrier. So let me give an illustration using a waveform. So say for example we have this waveform which is representing the modulating signal or the message signal, which is of course a low frequency signal. Carrier wave is a simple sinusoid, so you can see that this is a simple sinusoidal wave which represents the carrier. So we have a carrier and we have a message signal, and now what we want to do, we want to superimpose the information contained in the message signal by the carrier. So this representation here shows this amplitude modulation scheme. You can see that the region where the amplitude is high, we have increased the carrier amplitude, and the region where the amplitude of the message signal is low, the overall amplitude of the the carrier is reduced. So you can see that if I draw the envelope of this thing, if you follow the amplitudes, so these amplitudes, they are actually following the message signal. So by looking at the envelope, or by looking at that amplitude variation in the amplitude, you can estimate what type of carrier was there. So actually the information which is contained in this message signal is now represented by the change of amplitude in this modulated signal. This amplitude of the modulated signal carries the original information. So in this case, you can see that the amplitude of the carrier is varied, is changed in accordance with the message signal. So this type of modulation scheme is called amplitude modulation, because we are using the amplitude of the carrier to represent the information. In other words, the information is actually encoded in the amplitude of the carrier. So in order to recover the information, we have to look at the amplitude of the carrier signal which is received at the receiver side. It is not necessary that we always change amplitude, because we have other parameters as well, frequency and phase. So other possibility is that we can change the frequency of the carrier. So we can change the frequency again in accordance with the message signal. So how, if the message amplitude is high, we will increase the frequency of the carrier rather than amplitude. So amplitude would remain same, we would not change the amplitude of the carrier wave, rather we will be changing the frequency. So high amplitude in the message signal would be represented by high frequency of the carrier wave. In other words, the information would be encoded in the frequency of the in the frequency of the carrier signal. So let me show with this graphical illustration. Again, we have this amplitude modulating signal or message signal, which is a low frequency signal, and we have a carrier wave. So what we will do, we will be changing the frequency of this carrier and in such a way that the high amplitude of the message signal would be represented by high frequency in the modulated signal. So this is the frequency modulated signal which I have bordered here. So you can see that the high amplitude results in fast variation here. The fast variation show the high frequency, whereas this low amplitude is represented by relatively low variations, which represents that there are relatively lower frequency. So you can see that the amplitude of this entire signal is same. There is no change in the amplitude, rather the frequency is changing. You can see that the frequency is changing. Where the amplitude of this message signal is low, you would see a relatively low frequency here, and where the amplitude of this message signal is high, you would see a relatively high amplitude of this carrier high frequency of this carrier signal. So in order to recover the information at the receiver side, we have to look towards the frequency of the modulated signal, because the information is now placed in the frequency. The information content is represented by variations in the frequency. So the demodulator has to look at those variations in the frequency in order to recover the original information. So this type of modulation scheme is named as the frequency modulation. So in frequency modulation, the information is actually placed in the frequency of the carrier signal. So we are changing frequency in proportional to the amplitude of the message signal. Third case is the phase. Third parameter that we can exploit in representing the information is the phase of the carrier signal. So in similar way, as I said, for amplitude and frequency, the phase modulation or PM, phase modulation occurs when we change phase of the carrier wave in proportional to the amplitude of the message signal. So where you have high amplitude, that means you will be having a relatively bigger phase, higher phase, and where the frequency, sorry, amplitude of the message signal is low, you will be having a relatively smaller phase angle. So basically the information would be encoded, I'm sorry, it's wrongly mentioned frequency here. Amplitude is information is encoded in the phase. So variation in the phase are represented are representative of the information signal. So in order to recover the original signal, you have to look towards the phase of the received signal. So this is the illustration of the phase modulation. You can see it here. So at higher amplitude, the phase is relatively high. At low amplitudes here, the phase is relatively low. You must know that phase and frequency modulation, these two are related. Whenever there is phase modulation, frequency also changes, or whenever then there is phase modulation, frequency modulation, the phase also changes, because they are interrelated. You can see from here in this waveform, you can say this is the entire angle. So whether you change frequency or phase, the entire angle is changing. So entire angle is actually changed whether we employ phase or frequency. So these two are closely related to each other, these two modulation scheme, but the definition still holds, because we are defining on the basis of proportionality. So in frequency modulation, the frequency of this modulated wave is proportional to the amplitude of message signal. Phase is also changing, but that change will not be directly proportional to the amplitude of message signal. Similarly, in phase modulation, the phase of this modulated wave is directly proportional to the amplitude of message signal. Although frequency is also changing, but that change will not be a direct proportion, that will be some other relationship, but phase will be proportional to the message signal. Okay, so these two they sometimes jointly called angle modulation or exponential modulation as well. So you can see that we can use the carrier to represent the information simply by adjusting one of the parameter of the carrier such that that particular parameter is changed wherever the message signal is changing. So by looking at that parameter, you can easily see that what type of information is being transmitted. Similar situation is for the pulse modulation. For pulse modulation, again, the information is represented in the carrier by changing one of the parameter of the carrier. So we need to change at least one parameter so that our information is represented by that particular type of change. So in pulse modulation, the carrier is actually rectangular pulse. So that pulse is generally placed at a specific time duration, which is sometimes called symbol duration, or sometimes when we are talking about discrete time system, so this sometimes become the sampling duration. Okay, the carrier is a rectangular pulse, and that rectangular pulse can be characterized by three different parameters. Its amplitude, its width or duration, whatever you call it, or third is its position. So we can exploit any of these parameters to represent the message signal. Similarly, if similar to the continuous wave modulation, we name pulse modulation on the basis which type of change represents the information, or which parameter we use to encode the information. So if we change the amplitude of the pulse in proportional or in accordance with the message signal, in that case this is called pulse amplitude modulation, or PAM. If pulse width is changed in accordance with the message signal, in that case this is called pulse width modulation. Sometimes we call it a pulse duration modulation. So both of these, they represent the same thing, whether you call it pulse width modulation or pulse duration modulation. Our third category is that if we use we represent the position of the pulse to represent the information contents or message signal, in that case this type of modulation scheme is named as pulse position modulation, PPM. So let me graphically illustrate these three different types of modulation scheme. You can see it here. So we have signal which is represented here. So we have defined certain time durations. These dotted lines, they are representative of those time duration, or sometimes these are you can say they are the sampling intervals where we are getting the information of the analog signal. For pulse amplitude modulation, we will be using the amplitude of the pulse to represent the information signal. So basically the amplitude of that pulse would be in proportional to the amplitude of the analog signal. You can see it here. If the corresponding amplitude of the message signal is this point, so you would see a pulse which has a relatively smaller amplitude. But for the second pulse, because the amplitude of the message signal is increased, so this pulse has a relatively higher amplitude. You can see that the pulse is positioned at the start of each duration, these dotted lines. So each symbol duration represents the start of the pulse. So position is same. Each pulse is placed at the start. You can see for all cases the position remains the same. Width is also the same for all cases. All pulses, they represent the same width, but the amplitude is different for each pulse. You can see that. Similarly, if you see third category, the third point here, you would see that the amplitude is actually pulse amplitude is reduced because this point has slightly smaller amplitude. Similarly, the further reduce in the amplitude of the message signal will result in further reduction in the amplitude of this pulse. So you can see that the amplitude of each pulse is following the amplitude of the analog signal. So by looking at the amplitude of the pulses, you can estimate what type of changes were there in the message signal. Similarly, we can use the pulse duration modulation. In that case, the amplitude would remain same. You can see that all the pulses, they have same amplitude. Position would also remain same. We have placed all the pulses at the start of each symbol duration, but width is different. You can see that this pulse, if you compare this one with this one, because the second one has a higher amplitude, the message signal has higher amplitude, so the corresponding pulse has a relatively wider width as compared to this one. Similarly, if you compare this one with the last one, you would see that the last one has relatively shorter width, smaller excuse me. So the last pulse has relatively smaller width, whereas the one corresponding to the high amplitude has significantly wide pulse width. The same scenario is observable for the case of pulse position modulation. You can see that when we employ pulse position modulation, all the pulses they have very narrow width, they are all of same width, they are all of same amplitude, so they all has same amplitude. So we are not changing amplitude, we are not changing the width, rather we are changing the position. So if you see, this is the symbol duration, so this is the other symbol duration. The position is different for each amplitude. You can see that the smaller the amplitude, the pulse is placed closer to the start end, and the larger amplitude means the pulse will be positioned farther from the start of this symbol duration. So you can see that the position is changing. So as we are increasing the amplitude in this way, you can see that the position it is shifting towards the end of that symbol duration, and when the amplitude was decreasing, so the pulses they becoming closer and closer to the start of the this bit duration. So you can see that each position is actually indicating the specific amplitude of the message signal. So you can see that by using changes in one of the parameter of the pulses, we can easily convey the information that is contained in the message signal. So this was an overview how we represent signals by using carriers. So this was illustration of carrier continuous wave CW modulation, where we can exploit either amplitude or frequency or phase to represent the information, and this is the illustration of pulse modulation, where we can exploit either amplitude or duration or position of the pulses to represent the message signal. So in this slide I have summarized the different types of modulation schemes that we have discussed so far. So we have two major categories. One is called continuous wave modulation and other is called pulse modulation. So the main categories are these two. Continuous wave modulation can be categorized as linear modulation or exponential modulation. Exponential modulation means the angle modulation. So we can use the both terms, angle modulation. So linear modulation refers to the changes in amplitude, whereas the exponential modulation or angle modulation represents changes in angle of this the sinusoidal wave, and that change in the angle can come from frequency or phase. So we have two different types of modulation scheme, one is FM and PM, whereas change in amplitude can come in variety of different forms, although I haven't discussed them so far, but they are actually variations of this amplitude modulation. So all others, these are actually like subcategories of this AM modulation. So linear modulation is actually amplitude modulation. Similarly, pulse modulation can be categorized in three different categories: pulse amplitude modulation, pulse duration modulation, or pulse position modulation, as we discussed previously. So this was an overview of the modulation schemes that we will be discussing in this course, and of course so far I just tried to explain how the information is represented by using variation in the amplitude, and we will be discussing the mathematical form of each of these modulation scheme and physical hardware related to this modulation scheme, inshallah, in our subsequent lectures. Before we go further, we need to discuss few assumptions that will be taking care in the future lectures. So we will be assuming two important points related to our discussion regarding this signal xt, whatever message signal we are using. So we will be assuming that they satisfy these two conditions. First of all, the message signal is assumed to be band limited. Band limited means it has a finite bandwidth. So that means if you plot the spectrum of the signal, so here I have plotted the spectrum. This is the magnitude spectrum, and this dotted line is showing the phase spectrum. So you can see that the magnitude spectrum extends from 0 up to certain point, which is represented by W. So there is no frequency content beyond W. So if you see frequency above W bandwidth, so you would see that the amplitude becomes almost 0. So there is no frequency content. So this type of signal is called band limited. So because it exists in a specific band. So whatever message signal we will be discussing in our subsequent lectures, we will be assuming that they are band limited. That means they have a finite bandwidth, which is represented by W as here. Second, we will be taking this xt to be a normalized signal. Normalized signal means we will be considering that amplitude is less than or equal to 1. So the signal is represented like this. The magnitude will be the xt magnitude will be smaller than or equal to 1. Although it does not have significant impact on our calculation, because if any signal does not have less than 1, we can magnitude less than 1, we can simply divide it by that magnitude to make it equal to or less than 1. But using the normalized message signal would simplify our mathematical expressions. So that's why this is a common assumption. In case you do not have a normalized signal, you can simply multiply by the amplitude to get it denormalized. So in order to get the denormalized signal, you have to multiply it by the amplitude. Secondly, the signal power. Of course, if you know the amplitude, you can calculate the power as well. The power is actually average of the square. So x square t, this funny bracket here is actually show averaging operation. So this thing is this represents averaging. So wherever we will be using this notation, so this we represent that we are calculating a time average of this thing. So if we calculate the time average of x square t, that would be represented by the signal power. So of course, because we are normalizing the signal, so this average power would also be less than or equal to 1. So these are the two basic assumptions that we will be taking when we will be discussing different signals, and we will be developing the expressions for different modulation schemes. So I would stop this lecture here. So for today's lecture, I have tried to explain how the information is superimposed onto the carrier. So how we change the carrier to represent the message information, and also we have discussed few assumptions that will be considering when we'll move on to the mathematical analysis related to different modulation schemes. So this is all for the first lecture. Inshallah, from the next lecture we'll be starting individual modulation schemes, and we'll be trying to discuss different mathematical expressions and different concepts related to that particular modulation scheme. So thank you all.